Hello, everyone. Welcome to our hackathon info session. My name is Franziska,
And my name is Adam.
and we're extremely happy to have you here for today and for the hackathon. And today is really about informing you a bit about how the hackathon is going to run, who we are at CISPA, what we are doing, what kind of tasks you can expect, and how you can best prepare. So let me just get a brief kickstart on who actually is here talking to you. And we first have Adam. So if you want to go ahead, Adam, and introduce yourself.
Okay, so a bit about us, so who we are, and also what we do at CISPA. So first of all, my name is Adam Dziedzic, and I used to travel the world and do research in many different places. So on my list of places that actually I visited and worked in and did research with are Google, Microsoft, CERN, DTU, many places also in Canada, especially University of Toronto and West Institute. And then currently I am working at CISPA, where I am faculty member, and my research is actually primarily focused on trustworthy machine learning.
And my name is Franziska. And I also got around quite a bit for my research. I started my research career in Berlin, and then later on moved for my postdoc into Canada, where I worked at the Vector Institute and the University of Toronto on different topics of trustworthy machine learning. And now I'm a faculty at CISPA, where I co-lead the SprintML-Lab with Adam, and our research overall focuses on topics of trustworthy machine learning. Before we dive into the topic itself, let me just give you a brief introduction into CISPA. And you've all seen Germany on the map. We are roughly here, so relatively close to the French border. You can find our institute. Actually, pretty close from the location in Paris that we're going to have the hackathon in. So, taking the TGV train, you can reach us in less than 2 hours. And CISPA is a very international place that focuses on research on security and machine learning. And we currently have a bit over 600 employees from 52 different nations. And we have more than 40 faculty who work on extremely cutting edge topics of IT security and of machine learning and the intersection thereof. So if you're curious about any of this research afterwards, please, during the hackathon and also before and after, feel free to just reach out, drop us an email, and ask your questions. We are more than happy to tell you more about the Institute and potentially also find out what opportunities would arise here for you. And CISPA is not only doing IT security, but actually CISPA is the world best institute that does IT security. So if you look into CS ranking, which is the de facto standard on how institutes are ranked in terms of their research, for the area of computer security, CISPA is number one, as you can see, much above the elite US universities and everywhere. So it's really the place in Europe for IT security. And to give you a bit more insight into our lab, which is also heavily involved into designing the hackathon here and providing you with the tasks, we are the SprintML-Lab. That stands for Secure, Private, Robust, Interpretable, and Trustworthy Machine Learning. And at the moment, there are roughly 20 people behind the work, from the postdoc level to PhDs, masters, international visitors. And if you want to find out more about our lab and about the research that we are doing, you can always visit our website. And today you're going to learn more about some of the research we do, because this is also heavily influencing the tasks that you're going to face during the hackathon. And let's now dive in what you can expect on November 22nd and 23rd when we meet in Paris. We have the days planned roughly as follows. So, as you know, a hackathon is a roughly 24-hour event where you have the possibility to solve your tasks. And we'll be meeting on Saturday around 11, and you can register and get everything set up. And then we'll have some opening talks where we again give you some introduction, some information about the venue, some more insights on the potential task and what to expect. And then everybody can just dive into their topics, and then you can move into really like solving the tasks. We have food served throughout the hackathon, so we have dinner and breakfast here. And then once we are done, like roughly on Saturday around lunch, we're going to look into the scoreboard and we're going to see which team is the highest ranked, like which are the highest ranked teams, and those teams will then give a presentation eventually on how they did solve the tasks, and this will then influence like the final ranking. And at the end, we'll announce our winners and we'll have a small award ceremony. And as you know already, like the honors don't end in Paris, but if you manage to win the hackathon, you will also be invited to join our final here close to CISPA, where we will be having all the winning teams over our European hubs compete for the title of the CISPA AI European Hackathon Champion.
So maybe also a few words to this organization of the hackathon. So we already shared with you the initial information about potential reading that you should do before the hackathon. So what we actually indicated is topics that can really help you to understand the background about machine learning trustworthiness. And then also before the hackathon starts, before the coding, we will also have a presentation regarding the tasks. So also we will present to you what tasks you will be working on, and also there is also time before the hackathon itself for the additional questions regarding specificities of the tasks that we will be actually delivering and which you will be working on for the 24 hours on Saturday and Sunday in Paris in roughly 2 weeks.
And to give those of you who are here today a head start, we will give you a small introduction on the research that is behind the tasks. And like, we're not going to share the exact task with you, but the tasks are going to be in the environment of what we're going to present now. And this will give you also a rough idea on what you can potentially prepare for if you wanted to. And we'll be starting off by one of the classical topics of IT security and machine learning, which is adversarial robustness. So let me start by explaining a bit about like what adversarial robustness is all about. And I think you all know that machine learning models are extremely powerful and they can do enormous things. For example, if we give you this huge overview of all kinds of dog breeds that there exist, and then we ask you for this particular one, I wouldn't know, but the machine learning model is pretty confident that this is a Pomeranian. But then there's a problem because machine learning models can also be easily fooled. If we give the model this kind of image, the model would confidently predict that this is a panda. But the other image here, it's suddenly not so sure anymore that this would be a panda, even though both images for us human viewers look exactly alike. Both are a panda eventually. And the only difference that there is in these images is that the one has some adversarial noise added into it. So basically, we have an original panda image, and the model is decently confident with 57% that this should be a panda. But then, if we add carefully crafted perturbations to this image, it gives us something that for humans still looks like a panda, but the model is 97.7% sure it's a gibbon. So it's wrong, and it's like with high confidence wrong. And these kind of examples affect the use of machine learning in high stake applications, because you can now imagine if the model is able to misclassify such an obvious panda, basically. If we use machine learning model for autonomous driving and we present a stop sign and just like slightly modify that, then the model might also be able to just do a complete misprediction and tell us that it might have seen a speed limit. So, adversarial robustness is a severe threat to machine learning trustworthiness. And just to give you an intuition on what is happening, why the model is confidently like classifying our panda here as a gibbon. If you are in a normal model or with normal data, then you basically have the panda class and the gibbon class, and they're divided by the model's decision boundary. So, like everything that's on the left for the model is a panda, everything that's on the right is a gibbon. But what happens now if we carefully craft adversarial perturbations is that we can push the example here over the decision boundaries. But the question is, how do we find the right noise? Because if we just add random noise to any other direction, you'll see that the image won't change the class. So we need to really find the right noise. And how do we do that? To arrive there, let's just quickly revisit how we can like learn with machine learning models. And in machine learning models, we usually have some input data X and we have the model. And the image, like the inputs, the training images are usually frozen and the model itself can be changed, so it can be learned. And then how learning just goes is that the model does an initial prediction where it thinks that it's a panda by 30%. And then we calculate something called the loss. So the loss then tells us like what's the difference between the model prediction and the true label panda. And here it's basically the model is off by 70%. And then we backpropagate this loss through the model. So we tell the model how it needs to change the parameters to get more confident on like having a panda prediction here. And we do what's called the gradient descent. So the gradient gives us the direction of the highest increase, and we want to decrease the loss. So we do this gradient descent, and then the model learns iteratively and always improves, and over time becomes much more confident that it does see a panda bear here. Now, you train, of course, on multiple images usually, and then overall you just want to minimize the loss on all the images that you see. And for adversarial training, like finding the right adversarial noise is kind of a similar idea, just that this time your model is frozen because you have one model that you want to attack. And this time you say your image is kind of trainable or it's kind of changeable. And what you do is you infer the model through the image through the model, get a prediction, and then you calculate the gradients with respect to the image. So how would we have to change the image such that the model prediction eventually changes? And for us here, this time we don't want to do gradient descent, so we don't want to decrease the loss. But for adversarial perturbations, we want to increase the loss. We want to make the model mispredict. So eventually, this then gives us a gradient for every pixel of the image. How should we change the pixel to get more loss and to be less secure that it's a panda? And we do the so-called gradient ascent, and thereby then like get some adversarial example that will be like classified by the model not as a panda but as a gibbon anymore. This is the very basic and very naive way of achieving like adversarial examples. But what's the problem is that if we do this kind of just stupid gradient ascent, it will incur some perceptible changes into the model. So like the gradients are unbounded. So the image could change significantly. And even for a human observer, it wouldn't look like a benign panda anymore. So based on that, we should maybe specify what we actually really want. What we really want is that we want to find a perturbation. This means a noise, like the carefully crafted noise, such that the model predicts the level y, like is basically correctly predicted. But if we add this noise to the image, then the model does not correctly predict the image anymore. So it mispredicts. And we want to do all of that while keeping the perturbation r relatively small. So the perturbation should be bounded. And here, like the bound, like the perturbation should be smaller than epsilon, can be set in different norms. For example, we could have a max norm like over infinity. So you could think about this like as having some like unbound perturbation over the whole image. So you would basically bound the maximum absolute value in R. So for example, if you have the max norm in a vector that is 2 and minus 3, then like the max norm would just be the largest element in this vector. And in this case, this would be 3. And then we could say that we want no pixel be altered more than 3 here, or epsilon in our way. And there are different methods how we can achieve that. And the simplest method that has been proposed is the so-called fast gradient sign method, or FGSM. And in FGSM, what we do is that basically we do this kind of gradient step, but then instead of like updating with the entire gradients, it just takes the sign of the gradient. So all the negative numbers here become -1, and all the positive numbers become 1, and the 0 stays the 0. And so thereby we kind of like treat the loss as a linear function, and the gradient of the image just shows us in which direction we should change the pixel to get the misclassification. And in overall, we don't add only -1 or +1, but we multiply epsilon. So and then epsilon tells us basically change every pixel either by plus epsilon or minus epsilon. And as a formula, this looks kind of like this. So our adversarial example results from having the normal example, then plus epsilon times this matrix of ones and minus ones. And the epsilon is our perturbation budget. If we have a large epsilon, then of course the image is getting more likely misclassified. But if we have a small epsilon, the image will much likely look more like the original panda that we have. But then it's also like not 100% certain that we'll be able to misclassify. So then the question is, can we really decide what we want to misclassify for? So far, we've said, okay, we take an image of a panda, we add some noise, and then the model will say it's a gibbon. But we cannot really predict that the model will say that it's a gibbon, but it's kind of an untargeted adversarial. So we say the image can be misclassified to anything else apart from panda. But what we can also do is that we can have a targeted adversarial example where basically we decide which class we want to push the example to. So, for example, we don't want this to be classified as a panda anymore, but as a tiger. And what you can then say is basically you give the target label tiger, and the gradient will be calculated with respect to the loss of like maximizing the loss for panda and minimizing the loss for tiger. And thereby you can get the worst possible misclassification for this image as a tiger. And then like the limitations with FGSM is though that we are kind of limited by a single step. So we can update the image exactly once. And if the image crosses the decision boundary, then we are good. Then we have an adversarial example. We have successfully fooled our model. But if the decision boundary was to look like this, then our best step even wouldn't push us over the decision boundary. So we cannot really guarantee that we get some misclassification. And the second problem is that this FGSM attack is pretty sensitive to the step size. So our step needs to be large enough. So what you see here is obviously the step that we take is not large enough to go over the decision boundary. But if we have it like larger, then the image becomes visually much more distorted. So both is not ideal. And therefore, we do have some stronger attacks. And the next like attack that I would like to present is the so-called BIM method, the basic iterative method. And in this, we can craft adversarial examples with more complex boundaries. And BIM is very much like FGSM, but it takes many small steps instead of just one single step. And therefore, it helps in cases where FGSM fails. So basically, it defines like what is this region around here, and then it finds like where does the decision boundary cross such that we would misclassify. And at any time, like for a range of small steps, we just go into this direction of the decision boundary and then take the step and then we adjust and we look again in which direction is the decision boundary and we go there and we adjust and step and eventually we are there over the decision boundary and we have successfully fooled the model. And because we said that we want to have some like maximum perturbation to be not visible, then we need to clip back, which is what means that basically if we have gone a bit too far, if some pixels are now changed more than epsilon, we have to clip these pixels back to epsilon to just come into this epsilon area around the method. But the problem with BIM is that BIM can get stuck in a local minima. So what can, for example, happen is that we go into this direction here first, and then we clip and suddenly like we always go in that direction and never come out, and so eventually we still don't manage to fool the model. So overall we just need another method that is yet better, and what has been proposed is a so-called projected gradient descent, or called PGD, which always doesn't start at the same point, but it starts at random perturbations inside like this epsilon ball around the image. So instead of always starting from the perfect panda, it perturbs the panda first and then does this update. And so basically we add some noise here. And thereby we can explore different regions of the loss surface. So we would start here first and then there, and we would get it. So with that, PGD is a strong attack. But can we do something against it? So can we protect the models against being vulnerable? And one thing that we can do is the so-called adversarial training as a defense. And in adversarial training, it's about training the model such that it will become indifferent against the perturbations. So where a normal model just minimizes the loss over clean data, we now want our model to minimize the loss when we have a perturbation. So like we want the model to still correctly predict while we have kind of a maximum perturbation in this epsilon box. And this then gives us a robust learning objective where we still want to learn while maximizing our perturbation. And what this does over time is that it kind of alters the decision boundary. So instead of being vulnerable to the small perturbations, it just pushes the decision boundary slightly away from all the samples such that we cannot easily cross it anymore. and then the data points get still correctly classified and the model is robust to perturbations. So to sum up, we've seen three different types how we can attack the machine learning models with adversarial attacks from FGSM, BIM, and PGD. And they all have different setups with their strength varying based on like what they can do. And PGD is obviously the strongest attack with being adaptive and having different restarts. And we also saw that thereby we can fool models, but by leveraging the attacks to then retrain the models with like adversarial robustness in mind, we can achieve stronger robustness. And this was it for the first part. If there are any questions, like immediately, the chat function is enabled to ask the questions.
Also, actually check if there are any questions that evolved during this time. So you can ask the questions in the chat. There's also Q&A, so both of these options are possible to ask questions. Mhm. And also maybe in the meantime, also Franziska can also monitor the Q&A, and we can also see if you have any questions on the way, and please type them, and we can either answer them immediately or just at the end of the session.
Awesome.
Very great. So let's move on to the next part. So, okay. So let me now tell you a bit more about another pressing issue in AI. In this case, we want to identify what data was actually used to train generative models, and also to be able to trace what data actually comes out of or is generated by these AI models. So first of all, GPT models from OpenAI are capable of generating high-quality text with unprecedented speed and fluency. So beyond natural language, also these models can tackle complex mathematical problems and then even construct rigorous proofs. In the vision domain, Stable Diffusion models from Stability AI are able to produce photorealistic images that accurately adhere to detailed user prompts. Complementing these advances, models from Suno generate music tailored to match any desired emotional mood. These advances change how we write, what we see, and how we listen to. Generative AI models are trained on enormous amount of data that are scraped from the internet. These training datasets are very diverse and include news articles, books, visual artworks, and pieces of music. And this rich information is necessary for the high quality generation from these models. However, as the generative models are trained on massive internet data and generate high quality content, their inputs and outputs form so-called data loops. So recently, together with our students, we showed that the image generative models memorize and then reproduce verbatim some of their training inputs. Similarly, the text generative models were shown to memorize and then reproduce entire copyrighted books that were used for training of these models without the author's consent. It's particularly concerning that generative models are often trained on copyrighted data without permission. This is raising significant legal and also ethical concerns. In fact, currently, there are estimated to be about 25 ongoing lawsuits, such as OpenAI versus New York Times. The data loops cause misinformation, since the generated text, images, and music are often indistinguishable from human-created content, such as fake news. Another pressing issue is that the data produced by the generative models is published online and then scraped by model providers to reuse this data to train new models. This actually reinforces biases present in the previous model versions and replicates harmful content from initial data, and then results in the models having lower performance. To prevent this harm from generative models, European AI Act now demands that AI systems that create synthetic content must identify their training data and artificial generated outputs. This comes into effect on August 2nd next year. However, the current methods are not ready to fulfill these requirements. At the root of these key challenges of data provenance in generative models are three things. So first of all, we are not really able to easily identify which data went into the model's training sets. Second, we are also not able to verify which data points were memorized by these models. And finally, also we have to identify which actual data comes from these models. So what we can really do with all of these problems? And now we start from this major topic of how really this content is generated by generative models. So let us start from this standard, I think currently most popular paradigm of autoregressive generation. So here I presented initial version for the language models. Here we have example that we are given to the model initial prefix of a sentence, so she ate an, and then we ask the model to complete this next word. So in this case, the model predicts the new tokens and generates the new word being apple. And then here, what we really do is this unidirectional token prediction. And here we have on the bottom of the slide also the probability how we can compute for this given set of tokens for this given model. The main advantage of these autoregressive models is that they adhere to the scaling laws, meaning that with more compute, with more data to train the models, and also with the largest, with the more with the more larger models, actually, we obtain higher performance of these predictions. Also, just shown that these models actually generalize very well, and then even without training them on specific data. Now, how this really concept of autoregressive models transfers to the vision domain. So the latest breakthrough in the autoregressive models in the vision was so-called VAR model, which stands for Vision Autoregressive Model. And in this case, what we predict is the next scale for the given image. So we can think about this as an artist who draws a painting and he or she starts from a general concept and then steadily arrives at the image with very small details. So here in the same vein, we start from a very initial concept of the image with R1, in meaning scale 1, resolution 1. We produce the next scale, R2, R3, R4, and so on and so forth until the final image, in this case with the scale R sub k. And there are two training steps in this vision autoregressive models. In the first step, we have to train a multi-scale vector quantized autoencoder. So the autoencoder model starts with initial image, then it is transformed to a latent, and then we reconstruct the initial image from the latent. We take the initial image, then encode the image, and then the encoded image is turned into scales, these resolutions, with many tokens per given scales. Then the scales are unified into an embedding, and then we do the decoding of this obtained latent, and then we finally get the final image. So I'll explain in the next slides also in detail how this process works, and now we'll go to the second part briefly, which is about training the transformer model. So what we really also want is that once we get from the initial image to the encoding to the tokens, and we want also the model to be able to generate the next tokens, next scales from the previous ones. So for this task, we use the transformer model. Now let's focus on how we train this first part with the multi-scale VQVAE. So I'll show you the overview of this process starting from the initial image, in this case being image of a cat. We encode the image. Encoding actually is done with convolutional neural networks, and then we obtain the latent encoding of this given image. Also, we code this latent a feature map with, in this case, much fewer dimensions than the initial image. After that, we tokenize the representations. So actually what we do is that we quantize the given feature map into tokens. So what we really want to learn is a so-called codebook, which is a dictionary of in each entry 32 float values to be able to express these images through these tokens and be able to construct images token by token. Next, once we construct this image out of tokens, we then dequantize them, meaning that going back to the latent space, so we constructed feature map, and from the feature map we do the decoding back to the initial pixel space. So here in this case, we show how we can train this codebook to express the images through the tokens. Now, how do we train this var transformer to be able to predict next tokens from the previous ones? So we are given the start token S, we generate the first scale, here denoted as R sub 1 hat, and we compare this predicted R1 hat to the expected, meaning ground truth, R sub 1. And then, given these two scales with these tokens, we compute standard cross-entropy loss to be able to verify if the model can predict the expected tokens. Once we have this first scale with the tokens, we move on to the second scale. Now, with this regressive approach, we give to the model the whole prefix with the starting token and the tokens from the scale R sub 1, and then we ask the model to generate the next scale, next resolution, R sub 2. Again, model generates this resolution R sub 2 hat, this is the generated one, and we compare these tokens from the generated next scale with the expected ground truth tokens R sub 2. Again, we compute the cross-entropy loss and then backprop through the transformer to be able to better predict these tokens. So this is a very short overview of how we can generate images with regressive approach. And now let's focus on how then we can identify which images come actually from this given model. So now let us tell you more about generative models in the sense of how we watermark the outputs from these models. So in general, the question is a given image generated or not? So we are provided an image, for example, of a cat, and then we have to have some detector to be able to state if this given image is human created or model generated. However, in the natural form, it's really hard to predict. So currently with realistic images that the models output, we are really having hard time to verify if model actually this image created or it was really coming, for example, from a camera. Now, what is currently one of the most prominent approaches, popular, is to add watermark to a given image. So then when you generate an image from a model, you also add additional signs to this generation. You will slightly perturb the process to watermark the image, being able to give a small signature that actually this image comes from a given model. With that, it is much easier to detect if a given image was generated. But how do we really do this watermarking of images? So we already showed to you that we can generate these images in autoregressive models, scale by scale. And in the latest state-of-the-art models, what actually is happening is that these actually scales are expressed even by bits. So here we have these many different scales, and each of them is composed of many bits. Now the question is how we can really watermark such generation of images where we have bits in every single scale. So recently what we found is that we can enable identification of the content generated by this bitwise generation of images with a new watermark which is called bitmark. So actually this method embeds a watermark directly at this bit level at every single scale during the image generation process. And the bitwise watermark subtly influences these bits that are generated to preserve fidelity of this image, so quality of the generated images. At the same time, we want to stay robust against different watermarking removal attacks, or that somebody, for example, takes the image, applies, for example, compression of the image, and then will remove the watermark. So we want to be also robust against such image transformations. So the main goal is to influence the generation of bits by bits so that we can slightly nudge these bits and then add signature to this given generated image that actually this was generated. So how do we really do that? The watermark embedding is directly applied on the bit level in these regressive models. So first we separate the list of all possible bit sequences into so-called red list and the green list. So let's assume that the previous bit was 1, and now we want to generate the next bit. So we are given these two list of bits. And in this case, what we really want is that since we want to generate more green bits, we want to nudge the model to generate actually 1 as the next bit. So here we express what is the probability of generating bit 1. So we express probability through the logit. So model generates this logit for the next possible bit 1, and also analogously to the possible next bit 0. So this is how it is generated in the standard way, but now how can we slightly influence the model to generate bit 1? So here it is how we do that. So we slightly nudge the model to generate these sequences from the from the green list, so in this case bit 1, by adding to these softmax values this delta parameter. So here we see that this delta parameter slightly increases the probability of generating bit 1. And then this bit 0 is left as it was with this additional delta added for the bit 1. So in this case, we nudge this model to generate this bit 1 to be able to complete the green list. Okay, so let's move on to the next part. So how do we identify if a given image actually was generated, in this case also a watermark with our bitmark? So once we receive an image, we encode the image, and then actually then we create the tokens for the given image. And here our hypothesis, so-called null hypothesis, is that the sequence of bits is generated with no knowledge about the green and red lists, meaning that if the given image was generated from a given model without watermarking, then this number of green and red bits would be roughly the same. However, with our generation, what really happens is that we have slightly more green bits than the red bits. So what we really do is that we perform a statistical test based on this null hypothesis to verify if these bits that are in the given image are more towards the green list than the red list. Then if our actually test outputs a very small, in this case, t-value, then in this case we reject the null hypothesis and state that this image was actually generated by our model with the bitmark. Okay, so this is the part about watermarking the images, and then we can also tell you a few words about how to access the compute infrastructure. So during the hackathon, it will be of a big value for you to be able to solve the task on GPUs. And here we actually were provided with additional infrastructure for you to be able to solve our tasks. So actually this compute was provided by the Julish Research Center. This is a very generous grant from them that provides us with, I would say, plenty of resources to be able to solve the task from the hackathon. To give you some overview, what kind of resources you can expect during the hackathon, here we prepared a small list. So first of all, you have so-called compute nodes. We have, as of now, currently 40. And each compute node has 4 NVIDIA 800 GPUs. These are one of the most popular graphic cards, which are of high performance, and each of the GPU also have 40 gigabytes of memory. Additionally, each node has 128 cores and also 512 gigabytes of RAM memory. So these are the nodes that you would use for really the main experiments to find out solutions to our tasks. So once you develop the code, you can use these resources to improve your solutions to our tasks. Now, once you are able to log into this compute, you are on a so-called login node. These login nodes are usually used to develop the tasks, write the code, try small experiments, and they are equipped with 2 NVIDIA Quadro GPUs, RTX 8000, and also there are 128 cores, and then the memory size is 1024 gigabytes. So actually these login nodes are for everyone that uses this infrastructure to be able to start these jobs and also then request access to the compute nodes. Now, how can you really access these compute nodes? So let me walk you briefly through all the necessary steps from which you have to start until the point that you can log in to the given login node. So where we start from? You have to go to this website that is also here in the slide, but we also send to you the link to this website. You can just register. So you have to create a new account to be able first to log in to the Julish website. So once you go to this website, you click register, and then you are directed to the next step. So here, once you log in the first time, you have to actually set up so-called multi-factor authentication. Probably most of you use that for other services. But once you are there, just click on here. We also show exactly which button. And you have to set up this so-called MFA using one of the tools. For example, in my case, I use Authenticator from Google. Can be also free OTP. And there are plenty of other tools that actually are recommended to use for this step. Once you set up that, then you actually can go to the project website and also sign user agreement. So here there are some of the specific requirements to agree before you can use this compute. Now comes, I think, one of the most important parts. So to be able to log into the node, actually you have to provide SSH key. So you can either use your existing SSH key. Now for the Ulyss access for this compute, you are recommended. So we recommended using this SSH key based on ED 25519 algorithm. So here you can just either take your current existing SSH keys, just using something like cat command in the terminal, or if you don't have a SSH key, you can just generate that. There are plenty of tutorials how to do that. You just type in the terminal SSH dash keygen, and then you specify type of this key, being this ED 25519, then dash C, and you specify your email address. So these actually are the necessary steps to create or use your SSH key. Once you have the SSH key, then you have to just upload that. So there is a specific upload SSH public keys website. Here what we recommend is in this field your public key and option string. So actually maybe let me show you. This is this field. You provide your SSH key, and also you can additionally specify IP range from which you will log into these nodes, and then you add them and then click on start upload of SSH keys. Usually it takes roughly 15 minutes to be able to access the Ulyss infrastructure, but you have to be just patient after you upload the SSH key, and then just wait shortly before you can access the login node. If everything goes as expected, then you just type in your terminal this command, you specify your private key path, then actually your login to the Ulyss cluster, and then also this eureka.fz-ulyss.de, and then you are able to log into this login node. Here, also what you will be asked for is this um, authentication with the second factor. Here you just use the code from your tool, and then eventually you are able to access the node and then see what is the compute. You can just try a few initial jobs to be able to get used to this infrastructure and use this enormous GPU resources during the hackathon to solve the tasks faster or provide better solutions. So with that, let us move on to additional questions. If there are any, we are more than happy to answer them. Also, we have the Discord channel, so if there are any questions afterwards, you might think about what other questions come up later on, and we'll be there also monitoring Discord channel to answer your questions.
Also, you can ask your questions anonymously. That's why Adam has enabled the Q&A part, where basically if you type a question, it will not show your name neither to us nor to anybody else of the participants. And they'll just pop up here and we'll answer to them. Okay, it does not seem as if there are questions for now. We will be having an intro at the hackathon as well again, where we like then explain to you the exact tasks that you will be working on for the hackathon itself. And we'll be also mentioning again the compute infrastructure. But feel free, all the Jülich infrastructure is available online with documentation. So you can already check how you can best set up yourself. You can use the infrastructure also with your VS Code editor. So the better you are set up for accessing all the infrastructure, the quicker you'll be able to solve the task.
Actually, I have a first question from one of the participants. So from Daniel. Um, so you mentioned there was a problem with the current EU data protection. However, I didn't get the current problem. Can you explain it once again? Okay, perfect. A very good question. Thank you so much. So actually, in this slide, what I mentioned that so EU AI Act actually requires us to be able to mark the data that actually comes from generative models. So this um, directive from the EU will be uh, coming into effect next year. And what is really happening is that currently many of the model providers try to really come up with the ideas how to really watermark the outputs from their models. So this actually is required currently by the EU explicitly. And then what is really the problem is that the current techniques to watermark these models are usually not, for example, robust to watermark removal attacks. So one model can generate a given image, and then somebody might remove the watermark and actually show that actually this image was not generated. So what we actually need is more robust methods to watermark the outputs from the generative models. Second problem that actually is here also very, I would say, important is that these models are trained on a humongous amount of data. What is also required by the EU is to track what data actually was used to train the models. And then currently, most of these models actually do not really explicitly show what are the data used to train the models. And here, what we also want to potentially provide is a tool to verify or basically query if the given, let's say, data set was in the model's training set. So Daniel, does this question, does this answer address your question? Okay, thanks a lot for the question.
Okay, if there are no more questions for now, like feel free to reach out through the Discord channel, and you can just assume that those are basically the wider topics of trustworthy machine learning and AI and cybersecurity that the hackathon task will be situated in. So if you want to make yourself familiar, then it's recommended to look into those and also to check out the papers that we sent you.
So we can stay here maybe also like 2 minutes, and if there are no more questions, then after 2 minutes, we just stop the Zoom.
Otherwise, we already thank you for being here today, and we're very much looking forward to meeting you all in person in Paris. There's a question for the access to the Discord channel. Maybe you can send the link
Okay,
again to
perfect.
everyone.
So yeah, let me send you the link again. Um, so very good. Actually, now we have a link to Discord channel actually that is not expiring. So now you don't have to rush to be on Discord. You can just use this link, I think, literally forever. So I'll send this to everyone. So okay. So actually, once you click on the link, you will be directed to the Discord, and then you will be able to um, join this server on Discord and see also materials that actually we're posting, or you can also answer any questions that you have. Also, the session actually is recorded. We plan to upload this session and then share with you also a link to this recorded session. So one more question. What are the judging criteria for the project? It's a very good question. So how it usually is organized is that at the beginning of the hackathon, we give you tasks, and there are usually a few of them. I would say most frequently 3 tasks per hackathon. You work on the tasks through the whole hackathon. We also, during the hackathon, keep the scoreboard so you can see where your team is in the sense of like what is the best score for each given task and also across the teams. So you also see how good you perform during the hackathon. Then at the end, we reevaluate the tasks. So we have the final scoreboard. And then also for the best 7 teams, usually we give an opportunity to actually present your solutions. So also we have a committee that judges these solutions to the tasks. And then after your presentations, the committee meets and then it decides on the final list of the best teams. Then from these best teams, also we plan to invite 3 of them to also attend the final here at CISPA. So regarding the specific criteria, what we are looking into is that the best performing solution. So let's say if one of the tasks is that you have to find out what data point is in the model's training set, we give many such points, and then the more you provide confidence for the scores of the data points, so the better you identify which points were in the model's training set better than other teams, then you also have higher score for a given task on a scoreboard. So there is specific metric per task that actually can assess how well you solve the given task. And we have this kind of metrics for each task, and then the final score across teams. So how teams perform. So what are the teams that actually have the highest score across all of these 3 tasks? And then regarding also the final judging, so we also would like to see novel solutions that actually really performed well as well. And then, for example, if you at some point show that you had amazing solution, but maybe not enough time, also this might count as a very important contribution, the way how you uh, invented the solution. So we also take this into account, just in case, if, for example, if still these GPUs were not enough and you wanted just a bit more time to provide an excellent solution. So does it answer your question if these criteria are a bit clearer for the final evaluation of the tasks? Mhm.
All right. Then I think there are no more questions for today. So thanks everyone and see you in Paris.
Bye.
Bye.